Hello! Today we're going to be talking about an adiabatic flame simulation, and specifically how stoichiometry affects the energy that comes in and out of said simulation. So to begin, we have to talk about stoichiometry. Now, a flame, of course, produces heat as we combust natural gas, in this case, because we're going to be looking at a Bunsen burner as an example, with oxygen to create water and CO2. Now, the simplest hydrocarbon that can combust that we're going to be looking at today is methane, which is CH4. And when that combusts with oxygen plus O2, because again, oxygen naturally in the air is O2, that combusts, releases energy, and creates as a byproduct CO2 and H2O. We're going to need a little more space for that, so I'm going to erase that and scoot it over, plus H2O. Now again, because this is a little Bunsen burner, which I'm going to draw up here, there's a little flame up top, and here is our natural gas coming in, and here is our air coming in, and they combine up here and combust, and we get CO2 and H2O as a byproduct. Now, we know that because obviously the molecules coming in have to produce the molecules coming out, that mass must be conserved between them. So when we look at this, we start by balancing this equation, CH4 and CO2. Well, this has one C and this has one C, and those are the only C's in the equation, so it has to be a 1-to-1 ratio. Now, same thing with H4 from the CH4 and the H2, which means that for there to be 4 H's here, there must be 4 H's on this side, which means we must have 2 H2O's. That balances our C's and our H's. Now we look at our oxygens. For every O2 over here, we must have an equal amount of O's over here. So we have 2 O's, we have 2 O's, which is 4. So if we have 4 in total on that side, we have 4 in total in here, which means we'll need 2 sets of 2. So this right here gives us a balanced stoichiometric equation. However, we remember that the air we breathe in, that our Bunsen burner is pulling in from the surroundings as it begins combusting, is not pure oxygen. Air, AIR, is actually 21% oxygen and 79% nitrogen. So 21O, 71, I mean, technically there's also argon in there, about 1% or so, but for this simulation, just to make the fractions slightly nicer, we're going to do a 21 to 79 ratio to explain how oxygen and nitrogen coexist. Now, because every mole of oxygen, every 21 moles of oxygen comes along with 79 moles of nitrogen, we can actually add nitrogen to this list right here by saying that 79 over 21. For every mole of oxygen, there's this many moles of nitrogen, and since we have 2 moles of oxygen, or O2, we have 2 moles of N2, right there. And of course the N2 doesn't react with anything because it's just there, so we can just carry that over right here and say plus 2 moles of 79 over 21 nitrogen gas. So this is a balanced equation that describes the burning of methane in our natural gas. However, natural gas is not just pure methane. It is CH4, which is methane. It also contains ethane, which is C2H6, and even trace amounts of propane, which is C3H8. So because this burner will be burning all 3 of these, we're going to have to balance all 3 of these stoichiometric equations as well to figure out how much we're actually both of oxygen and nitrogen and also just total products produced. So we're going to do the same thing, but for C2H6, C2H6 plus blank O2 gives us, I'm going to leave a little more space this time. I don't need to draw the arrow so big since I'm going to need a bit of room over there to write later. Produces blank CO2 plus blank H2O. And we also know because of nitrogen, we're going to have blank, the same number of moles, 79 over 21 of nitrogen gas, and that's going to carry over as well and give us plus that same number of 79 over 21 nitrogen gas. Now we look at this and we say all the C's over here and the C's over here have to match. We have 2 C's, which means we're going to need 2 C's here. We have 6 H's. We're going to need 3 of these to make these 3 sets of H2 is 6 H's. So our hydrogen and our carbons are balanced. Now everything else the remainder of it tells us how many oxygens we need. We see this has 4 and this has 3, which means we have 7. Because this comes in sets of 2, we're going to need 7 halves oxygen as a bimolecular natural state, which means we're going to need 7 over 2 here, 7 over 2 here, and this balances our formula for the ethane that we're burning. Now, I could do this a third time for propane, which I could, but if we notice there's a pattern here that we always balance the C and H's first, and then whatever's left tells us how much oxygen we need. And because of that, we can actually generalize it into a formula for simple combustion. So the general formula is, I'm just going to write it in a more simple way. Instead of actually by an equation, we can show the similarity. We notice that for however many carbons we have in our hydrocarbon, we always have that many number of carbon dioxides. 1 CH4 is 1 CO2. C2H6 gives us 2 CO2. So the number of carbons tells us the number of CO2. And we can say the same thing about the H's and the H2O's. Because every H2O contains 2 hydrogens, and our hydrocarbon has some even number of hydrogens, we always know that the number of hydrogens determines the number of H2O, the amount of water produced, is half, or I guess this is double, so I could say, oh man, this is a very chalky eraser. Sorry about that. Number of hydrogens, I'll just say over 2 gives us the number of H2O that we need in here. And of course, oxygen is going to be whatever's left because both of these molecules contain oxygen, but oxygen here is only contained by O2. So when we look at this and we see that carbon dioxide has 2 oxygens, and we see that water only has 1, which means that added together, twice the number of CO2s and a single times the number of H2Os will tell us how much oxygen we need. If we see right here, we have 2 times 2 is 4, plus 3 is 7, divided by 2 is our oxygen. So in that way, we can say double our CO2 plus our H2O divided by 2 gives us our O2. So I'll say, I'm going to start abbreviating it by the molecules they give because it's a little bit easier. So if I say 2 CO2, which this represents the number of CO2, plus our H2O, our amount of water, divided by 2, because again, that would give us the total number of O's, and O's are coming in packages of 2, that's going to give us our amount of oxygen, O2. That's a little messy, but it's fine. And finally, the last thing we have tagging along is our nitrogen, because we know that for every 21 moles of oxygen pulled in by the air, there's an equal 79 moles of nitrogen that are getting pulled along as well. So we can simply say that the number of O2 times 79 over 21, because again, that's the mole ratio between them, is going to give us the number of nitrogens. A little scribbly because we're near the end of the board over here. But these are our rules. For any sized molecule, any sized hydrocarbon doing simple combustion, we can find that these ratios hold true. Again, I can really quickly prove it down here for propane, C3H8, that's going to give us CO2. We have 3, so we're going to have 3 CO2s. We have 8 H's, so we're going to have 4 H2Os. And because right here we have 3 times 2, I'll just get out of the way, 3 times 2 is 6, plus 4 is 10. 10 divided by 2 is 5, plus 5 O2. And we see, let's check this balance, 3C, 3C, 8H, 8H, 10 O's, 6 plus 4 is 10. It balances. And of course we're going to have plus 5 times 79 over 21 moles of nitrogen, which carries along plus 5, 79 over 21 nitrogen. So we can see that these rules hold true. So instead of actually thinking about how we're doing the stereochemistry, doing the stoichiometry, the words are very similar, and I'm chem right now, so that kind of thing happens. Anyway, without actually thinking about the stoichiometry, just by following these algorithmic rules, we can balance any simple equation of combustion. Now, what's important is, for the purposes of our simulation, we're going to assume that we're not only taking all of the air necessary, all of the O2 and N2 necessary to cause this combustion to happen, but we're actually adding an excess 20% air. So, what does that mean? Well, we're going to have to calculate an excess that we're lumping in with the rest of this equation. And just like nitrogen, which isn't reacting, simply gets carried through, this excess is also carried through and does not affect the reaction itself. If it doesn't affect the reaction itself, you may be wondering, Ethan, why do we care? It's going in and it's going out, and it's not actually reacting or generating any heat for this reaction, so why do we have to worry about excess air or not? And the answer is because even though it's not affecting the reaction, it is still heated by the reaction. All of the heat, all of the flame, all of the heat generated by this combustion still has to warm up these moles of nitrogen even though they're not reacting. And any excess air that flows through this tube is also going to be heated by the reaction, and so will draw heat away, lowering the overall temperature of the flame. So, how to calculate the 20% excess of air? Well, that's pretty easy. If we know how much air is going in, for in this case 5 moles of O2 and 5 times 79/21 of nitrogen, we know that 20% of this is going to be excess. So to do that, we're going to do a big plus. I'm going to do that just to show, just to separate. Plus for the excess, EXC, we're going to have 20% of both of these in addition. Now, 20% can also be written as a fraction as 1/5. So since we have 5 moles over here, it would be 5 over 5 moles of O2 plus 5 over 5 79/21 of nitrogen. That would also be carried over. Now, because obviously this is 5 and this is 5, it works out to cancel to say we have an extra mole of oxygen and an extra 79/21 moles of nitrogen flowing through for the case of propane. However, it carries for both of these. We'd have an extra 2/5 and an extra 2/5 79/21. And down here we'd have an extra 7/10 of oxygen and 7/10 times 79/21 of nitrogen. So I'll just write down the rule for excess right beneath the actual excess calculation, where we can see that the number of excess moles, number of excess air is equal to, well, that's simply the moles of oxygen and the moles of nitrogen times its factor. So we can just worry about the moles of oxygen, because if we take care of it in the moles of oxygen, since the moles of nitrogen is just the moles of oxygen times its like air ratio factor, we don't have to worry about it. So we can say the amount of excess air is actually equal to 1/5 the moles of oxygen, 1/5 O2. Because again, 5 oxygens, 20% of that is 5 divided by 5, which is 1. So the moles of oxygen we have in our equation divided by 5 will give us the amount of excess that we have to add in. I'll just draw an arrow to signal that's the excess. The amount of excess that we add in that's going to draw heat away, which I'm going to write here, draw heat away, which means our overall temperature, T flame, is going to decrease as a result of these molecules, this excess air stealing heat. So because of those moles of excess air, we're going to significantly affect the temperature of our flame, and of course by varying the amount of air going in and out in excess, will raise or lower the temperature accordingly. So thank you, and have a good evening.